Welcome to the Gravel Ride Podcast. I'm your host, Randall Jacobs, and our guest today is Craig Calfee. Craig is the founder of Calfee Design, the innovator behind the first full carbon frames to race in the Tour de France, the originator of numerous technologies adopted throughout the cycling industry, and on a personal note, has been a generous and consistent supporter of my own entrepreneurial journey. I am grateful to have him as a friend, and I've been looking forward to this conversation for some time. So with that, Craig Calfee, welcome to the podcast.
Oh, thank you. Nice to be here.
So let's start with, what's your background? Give your own story in your own words.
Well, I've always ridden bikes. I mean, as a kid, that's how I got around. And that's as you become an older child, you find your independence with moving about the world. And a bicycle, of course, is the most efficient way to do that. And later on, I was a bike messenger in New York when I went to college. And that kind of got me into bike design as much for the desire to make a bike that can withstand a lot of abuse. And later on, I used a bike for commuting to work at a job building carbon fiber racing boats. And during that time, I crashed my bike and needed a new frame. So I thought I'd make a frame out of carbon fiber tubing that I had been making at my job. So this is back in 1987, by the way. So there were no YouTube videos on how to make your own carbon bike. So I pretty much had to invent a way to build the bike out of this tubing. And at the time, there were aluminum lugged bikes, and I knew already that aluminum and carbon fiber don't get along very well. So you have to really do a lot of things to accommodate that. And the existing bikes at the time were, I would say, experimental in the fact that they were just trying to glue aluminum to carbon, and it really wasn't working. So I came up with my own way and built my first bike, and it turned out really well. And a lot of friends and bike racers who checked out the bike said I really should keep going with it. So I felt like I discovered carbon fiber as the perfect bicycle material before anyone else did. And actually, right at that time, Kestrel came out with their first bike, the K1000 or something. Anyway, that was in 87, 88, and I felt like I should really, give it a go. So I moved out to California and started a bike company.
So just to be clear, you were actually making the tubes. You weren't buying tubes. You were making the tubes out of the raw carbon or some pre-preg carbon, and then you came up with your own way of joining those tubes.
Yeah, I worked on a braiding machine. So it was actually a 100-year-old shoelace braider. From back in Massachusetts, there's a lot of old textile machinery, and braiding is, you braided socks and, nylon rope is braided. Mm-hmm. So this is a 72 carrier braider, which means 72 spools of carbon fiber are winding in and out, braiding this tube. And you just run it back and forth through this braider a few times, and now you have a thick enough wall tube. I developed a mandrel and tape wrapping method at that job and came up with a pretty decent way to make a bicycle tube. So that was kind of the beginning of that. And since then, I've explored all kinds of methods for making tubing, mainly through subcontractors who specialize in things like filament winding and roll wrapping and pultrusion, all kinds of interesting ways to make tubing. And that does relate to kind of an inspiration for me where I realized that carbon fiber, high performance composites are relatively young and new in the world of technology, where metals are, the metals have been around since the Bronze Age. I mean, literally 5,000 years of development have happened with metals. Carbon fiber, high performance composites have only really been around since World War II. So that's a huge gap in development that hasn't happened with composites. So that to me felt like, there's some job security for a guy who likes to invent things. So that was my kind of force to get me to really focus on composite materials.
Were you that insightful in terms of the historical context at the time, or is that kind of a retrospective reflection?
I don't know. I think I may have read about that. I had a friend who had a library card at MIT, and I pretty much lived there for a few weeks, absorbing every master's thesis and PhD thesis on bicycles that they had in their library. And I think somewhere in there was a topic on composites and comparing the technology of composites. So I probably got that from some reading I did. Or maybe I did invent that out of thin air. I don't remember. But nonetheless, the fact of it is, not a whole lot of mental energy has been put into coming up with ways of processing fiber and resin compared to metal. So to me, that just opens up a whole wide world of innovation.
Mm. And so the first frame was that you were creating essentially uniform tubes and then mitering them, joining them, wrapping them as you do with your current bamboo frames, or what was happening there?
It was more like our carbon fiber frames were laminating carbon fabric in metal dies, and
Hmm.
those are mitered tubes fitting into the dies. And that's a process I got my first patent on. And so in the process of compressing the carbon fabric against the tubes, you end up with these gussets in what is traditionally the parting line of a mold.
Hmm.
And
Hmm.
rather than trim them off completely, I use them as reinforcing ribs.
Yeah. Yep. Okay, so that explains the that distinctive element that continues with your some of your uh, tube to tube uh, frames currently, where you have
Yeah,
them. Yeah.
and the hand wrapping technique from that you currently see on the bamboo bikes came from developing a tandem frame, or basically a frame whose production numbers don't justify the tooling cost. So that's hand wrapped. That's just literally lashed together.
Hmm.
And a point of note there is I was a Boy Scout growing up, and there's this merit badge called Pioneering Merit Badge. And I really enjoyed Pioneering Merit Badge because it involved lashing poles together with rope. And you had to do with this one project, and I did a tower, and it was this enormous structure that went just straight up like a flagpole. But it involved a bunch of tetrahedrons stacked on top of each other and lashed together, and culminating in a pole that went up. I don't remember how tall it was, but it was really impressive, and everybody thought, "Wow, this is incredible." Stack of poles and some rope, and here we have this massive tower. So anyway, I was into lashing things together since a young age, and so I immediately came up with the lashed tube concept, which is where now the bamboo bikes are. Of
Mm.
course, there's a specific pattern to the wrapping, but the concept is basically using fiber to lash stuff together.
Well, it immediately brings to mind what's possible with the current generation of additive production techniques. Whereas before you could make small components and then lash them together to create structures that otherwise aren't manufacturable. Now you'd be able to say print it out, though those printed out materials don't have the performance characteristics of a unidirectional carbon of the sort that you're working with currently.
Right.
So we've gone deep nerd here. I'm gonna pull us out and say, okay, lots of time for this. This is gonna be a double episode. So next up, let's talk about how those frames saw their big debut.
Yeah. So we started making custom geometry frames in about 1989 and started selling them. And so big and tall, and the idea of custom geometry frames was pretty esoteric, and the pro racers were using a lot of custom frames. So Greg LeMond was in search of a carbon fiber custom frame builder in 1990, and no one really was doing it. We were literally the only company making custom carbon frame bikes. So he found out about us, effectively discovered us, shall we say, and it didn't take long for him to order up 18 of them for his Team Z teammates. He was sponsoring his own team with the Le Mans brand, so we didn't have to sponsor him. He basically paid for the frames, and put his name on them, and now we're on the defending champions Tour de France team. So that was a huge break, obviously, and it was really a pleasure working with Greg and getting to know the demands of the pro peloton. That really launched us. So that was quite a splash, and it always is a great answer to the question, oh, so who rides your bike, kind of thing. And you have the full on best one in the world at the time. So that was a fun thing.
And the name of the company at the time was?
Carbon Frames.
Yeah. So anyone
Yeah.
wanting
And
to dig up the historical record.
It's just too generic. And the other related to what you're talking about, the adventure bikes. So yeah, we had to stop. I mean, Carbon Frames was a terrible name because everyone started talking about all carbon fiber frames as carbon frames. So we thought that was cool, like Kleenex. And then we came up with the adventure bike, a very early adventure bike. And it was just, we called it the adventure bike. And now there's a classification called adventure bikes that, so again, I think we went too generic on how we named our models.
I've drawn from the rich tradition of Greek, philosophy for naming my own companies and the like.
Yeah.
And then next up, so you've worked with Greg LeMond on those frames. Carbon Frames is up and running, and you're producing custom geo frames, and you're starting to get at some scale at this point and some notoriety. Next up, you were working on your bamboo bikes. Why don't we talk about that?
Yeah, that was a kind of at the time it was just a way to get publicity. So at the Interbike trade show, you'd have a few creative people making some wacky bikes out of beer cans or other just weird things, just to get attention, just to send the media over to your booth to take a picture of some wacky thing that you're doing. So I thought, yeah, we got to do something like that to get some attention. And so I was looking around for some PVC pipe. Maybe I was going to do a PVC pipe bike, and I wasn't really sure, but I knew that we could just wrap any tube and make a bike out of literally anything. So my dog was playing with some bamboo behind the shop. She was a stick dog, so she loved to clomp onto a stick, and you could swing her around by the stick. She's a pit bull and lab mix. Anyway, we ran out of sticks because we only had one little tree in the back, but we did have some bamboo. So she came up with a piece of bamboo, and I was swinging her around by it, expecting it to break off in her mouth because I just wasn't really aware of how strong bamboo was. But it turned out it was really quite strong, and I thought, oh, let's make a bike out of this stuff. And sure enough, the bike was quite a attention getter. It got the quarter page in Bicycling magazine, so that mission accomplished on that front. But the bike itself rode really well. When I rode my first carbon bike, the very first ride on my very first carbon bike, I was struck by how smooth it was. It had this vibration damping that was, just super noticeable. And that really kind of lit a fire under my butt, thinking, wow, this is really cool. When I built my first bamboo bike, I had that same feeling again, how smooth it was. It was amazing for its vibration damping. So I knew I was onto something at that point. That first bike was a little too flexy, but the second bike I built was significantly stiffer and was an actual real rideable bike. So yeah, from that point, we just started building a few here and there, and it was still a novelty item until about 1999, 2000, when a few people who had been riding them were like, I want another one. I want a mountain bike this time. So it was just starting to get known, and we started selling them through dealers. And I mean, there's a lot of stories I can tell on how that evolved and how people started actually believing that a bamboo bike could actually exist in the world. So it took a while, though.
I think there's a whole thread that we could tug on maybe in a subsequent episode where we focus just on the bamboo bike revolution.
Yeah, that's there's a lot of lot of stuff going on there. I'm actually writing my second book on the history of the bamboo bike because there's so many interesting angles to it, particularly in Africa.
I'm struck by the juxtaposition of this bleeding edge, high tech material that you pioneered, and then this going back to one of the most basic building materials that we have, and building bikes out of that. And in fact, on the one hand, there's this extreme difference in terms of the technologization of each material, but on the other hand, there's a parallel in the sense that like carbon in tubes is best, generally when it's unidirectional, with maybe some cross fibers in order to prevent it from separating. And bamboo also has that characteristic of having, unidirectional fibers that are bonded together by some other material in the bamboo.
Yeah. Yeah, there's a lot of similarities. I mean, bamboo is amazing just because it grows out of the ground in tubular form, and it grows in a huge variety of diameters and wall thicknesses. So if you're looking for tubing, I mean, you don't have to go much further. It's just amazing that it literally grows out of the ground that way.
Just to paint a picture for folks too, most of our listeners, I'm guessing, are in North America or other English-speaking parts of the world. When I lived in China, and as you've been, you see huge scaffolding, multi-story, big buildings, and the scaffolding isn't made out of metal; it's made out of bamboo lashed together with zip ties and pieces of wire. So it really speaks to the structural strength of the material and reliability of the material, and should instill confidence when descending down a mountain.
Oh yeah. No, I remember seeing bamboo and scaffolding many, many years ago. And I thought, well, of course. And the other reason they use it in scaffolding is when a typhoon hits and it kind of messes up the scaffolding of a construction site, they're back to work on the bamboo construction sites much faster than the metal scaffolding sites, where they have to deal with bent and distorted metal scaffolding. To replace those and fix that takes a lot longer. Where bamboo, they just bend it back and lash it back together. It's so much easier.
There's one more thing on this theme that I want to pull out before we move on, which is talk to me about the sustainability component of it, starting with how it was done initially, and then now with, say, like biodegradable resins or other materials. Like, can this frame be composted?
The short answer is yes. The frame can be composted, and the other cool thing is if you take care of it, it'll never compost, meaning you can prevent it from being composted naturally. But if you really want to, dispose of the frame, it will biodegrade much faster than any other material that bicycle frames are made of. So yeah, the renewable aspect, the low energy content of it's utterly the best you can imagine. And we're kind of waiting for the world to finally get serious about global warming and start to have some economic incentives for buying products that are in fact good for the environment. We haven't seen that yet, but we're kind of holding out and hoping that happens, and then we'll see probably some significant growth in the bamboo adoption in the bicycling world.
I want to plant a seed that started to germinate in my head, which is this idea of bamboo as being the ideal material for kind of more mainstream utility bicycles and recreational bicycles. And really, it's a matter of the unit economics and economies of scale and consistency of material, which you could make uniform by having highly controlled grow conditions and things like that. But it could be a very localized industry too. Anywhere where bamboo grows, this could be produced, which reduces transportation costs, reduces issues of inventory carrying and all these things. So let's park that. I want to ask you more about the economics of bamboo in a side conversation to see if there's something to explore there.
Well, there is. I mean, that's what we did in Africa. Same concept as why would bamboo work in Africa better than the imported bikes from China? So that was the whole thing around that.
Oh, I love it. All right, so there will be a bamboo episode, folks. Uh, we're gonna continue because there's a lot of ground to cover here. So next up, so you've done the first carbon frame in the Tour de France. Carbon frames is up and running. You've started getting into bamboo. What was next?
Then lots of smaller developments, which have become really important to us from a business perspective. Carbon fiber tandem, we built the first one of those, and then we went to a lateralist tandem design, and it's pretty optimized at this point. So I would say we are the leader in the tandem world in terms of the highest performance tandem bikes. And then repairing of carbon frames. That was a big one, which we were kind of pushed into by our customers and other folks who heard that we could repair the Calfee frames, and they would call up, and literally we had one inquiry per week, if not more often, about like a Colnago that this guy wanted to repair, and he heard we could do it on ours, and we're like, well, buy a Calfee, don't, I'm sorry, but we can't repair somebody else's frame. You'll have to buy one of ours, and then you'll know that if you crash it, we can repair it for you. He was trying to make that a advantage for our brand, but we couldn't really, do that. So we said, well, if we can't beat them, we'll repair them. And we repaired a Colnago first, and then onto some Specialized, I think, after that. So we accepted repair jobs, and pretty soon it became about a third of our business. And it's of course now lots of other people repair frames, but we started doing that in 2001 or something, and we've been doing it ever since. And that part's been really interesting to see because we get to literally see the inside of everyone else's frames and look at the weak points. They often show up on people's frames, and we get asked to fix them or even redesign them at that point. So that's been really interesting to me as a technician.
And I want to come back to this in a second, but before we lose it, what is a lateralist tandem design?
So traditional tandems had a tube that went from the head tube, usually straight back down towards the dropouts or stoker bottom bracket, and it's a way to stiffen up a frame that's inherently not very stiff in torsion. But with composites, you can orient the fiber in torsion to make a tube significantly stiffer in torsion than, say, a metal tube of similar weight. So we were able to go a little bit bigger diameter and more fiber in the helical angled orientation and make a tandem stiff enough in torsion and get rid of that tube. And for a carbon fiber frame, that was really important because the number of times you have to join the tube, the more expensive it is, or the more labor content there is. Mm-hmm. So we were able to reduce our labor content, make the frame lighter, and make it stiffer all in one design change. So that was a big revelation. And now I think most of them have copied that design. So it's another time where we did something that now became the standard.
Yeah, one of many from what I've observed and read in the history. So around this time, or shortly after you started the repair business, you started doing some pretty wild frames in terms of pushing the limits of what was possible. Why don't we talk about that?
Yeah, we've done a lot of different types of frames, mostly for show, but like the North American Handmade Bike Show is a great venue for just doing something way out of left field. We did a bamboo bike made all out of small diameter bamboo. I only made one because it was a total pain in the ass to make. And it was also kind of inspired by a request from a guy who was not only a fan of bamboo, but he was a fan of Moulton style bikes. Those are the truss style frames with small wheels. So we built one of those and with only small diameter bamboo. And we built another one that was a real art piece. So just having fun with that from a completely artistic direction is a lot of fun for me because that's my formal training. I went to art school and learned about different materials and art and composition. Uh, and I was into the structure of materials and how they relate to each other. And so my art was more of a form follows function kind of inspiration. And so some bikes that I've made were are not terribly practical, but just explore the limits of structure. So another bike I made, we call it the spider web bike, which was literally a bike made of just carbon fiber strands, no tubes. And it was kind of wild looking, and a collector ended up buying it, which is really cool. But you look at this thing and you just couldn't imagine that it you could actually ride it. But it actually does ride fairly well. It's a bit fragile. If you crash it, it would be kind of dangerous. But stuff like that. I like to do that occasionally.
Think of like biomorphic design or like hyper
Yeah,
optimized design that maybe doesn't have the resiliency, but within very strict parameters will perform higher than anything else that you could create.
absolutely. Yeah, those are really fun. I mean, I'm really inspired by natural forms, and uh, the some of the new computer-aided techniques for designing are right in those lines. And so, yeah, I follow that pretty closely.
Little sidebar. I don't know if you've know of Nick Taylor, the guy who created the Ibis Maximus in front of the Mountain Bike Hall of Fame.
No, I don't think so.
I'll introduce you to his work at some point, but he's another one of these people who, very avid cyclist, is not in the bike industry, but is does a lot of trail building and the like, and is a sculptor really focused on the form of biological shapes and materials and things of
Hmm.
this sort. I think that there's a lot. I'm actually curious to dive more into your non-bike artistic work for a moment,
Hmm.
and how that got infused into your work with the bike.
Yeah, so I haven't done a lot of, just pure fine art sculpture in a long time, but when I was doing that, I was doing a lot of things that would fool the eye or s- take some material and push it to its limit. So I was doing stuff that was uh, you know trying to create a almost like a physical illusion, not just an optical illusion, but a physical illusion, or like how could you possibly do that kind of thing. That was a theme of my sculpture shortly after Pratt. So, for example, just take one example of a sculpture that I actually got a lot of credit for in classes at Pratt. It was a big block of oak. It was a cutoff from a woodworking shop. It was about a foot in, let's say, a foot cube of oak, and I raised the grain on it with a wire brush, and then I block printed on oak tag paper some black ink on rolled onto the oak block and made basically a print off of each face of the block. And then I carefully taped that paper together to simulate a paper block of the oak chunk that I had. So now I had a super light paper version of the oak block, and then I hung them on a balance beam, which I'd forged out of steel. But the hanging point was way close to the oak piece. And if you looked at it from 3 feet away, your brain would just start hurting because you couldn't figure out how is this even possible. And because it really looked amazing, super hyper real. Anyway, it just looked amazing, and it was fun to get the effect of how the hell did he do that? What's the trick here? There's something going on that's not real, or it's not physically possible. And I kind of got that feeling with the carbon fiber bike. When we built the first bike, everyone would pick it up and go, "Oh, that's just too light. It's not even a bike. It's a plastic bike. It's going to break instantly." So that was sort of a relation from those days to the bike.
You ever come across Douglas Hofstadter's book, Gödel Escher Bach?
No, but I'd be interested to read it.
Definite shortlister. You've come across MC Escher. of
Oh
course.
yeah.
Yeah.
Mhm.
And are there any parallels or any inspiration there?
Um, Not very direct, I'd
Okay.
say. Yeah, but
Who are your inspirations, or what would you say your creative energy is most similar to?
I'd say Buckminster Fuller.
Mm,
Yeah,
yeah.
I I studied his work in depth. Not only the geodesic dome stuff, but also his vehicles, the Dymaxion vehicle,
Hmm.
and the yeah. So there's a bunch of stuff that he was involved with that I'd say I'm parallel with as far as my interest goes.
What book should I read?
All of them.
Where do I start if I have limited
Yeah,
time?
yeah, it's a tough one. He's actually really difficult to read too. His writing is not that great. I pretty much look at his design work more than his writing.
Okay. So
His writing is
whose book
really
about Buckminster Fuller should I read?
good question. I'll catch up with you on that later because there's a
Yeah.
few of them that are worth a look.
Awesome. 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 Let's talk about 2001, your Dragonfly.
Yeah, the Dragonfly was an interesting project. It was so Greg LeMond had asked me like I want an even lighter bike. He was constantly pushing on the technology. And I said, well, there are some really expensive fibers that are starting to become available, but this would be a $10,000 bike frame, and it's only going to be a half a pound lighter. And he said, well, I don't care. I just, I need it for racing. I mean, when I'm climbing Alpe d'Huez with Miguel Indurain, and if he's got a lighter bike than I do, then I'm just going to give up, in terms of the effort. So he needs to have that technical advantage or at least be on the same playing field. So the reason why he'd spend, $5,000 for a half a pound of weight savings was pretty real. So, but it took until about 2000, 2001, after he had long retired, to really make that happen. So the fibers I was talking about are really high modulus fiber that was very fragile, too brittle really for any use. So we came up with a way to integrate it with boron fiber. It actually was a material we found through specialty composites out of Rhode Island. They do this commingled boron and carbon fiber hybrid material, which was they were looking for use cases for it, and the bicycle was one of them. So we built a prototype with their material, and it turned out to be not only really light and really strong, the the boron made it really tough. So carbon fiber has the highest stiffness to weight ratio in tension of any material you can use. Boron is the highest stiffness to weight ratio in compression as a fibrous material that you can integrate into a composite.
Mm.
So when you mix them, you now have a combination of materials properties that are just unbeatable.
It's like concrete and rebar almost, or
Well,
not quite.
I'd say that's a good analogy for composites in general, but now we're talking about the extreme edge of performance, where we're looking at the most high performance material for certain conditions, compression versus tension. These are conditions that are existent in a bicycle tube all the time. So one side of the tube is compressing while the other side is in tension as you twist the bike, and then it reverses on the pedal stroke. So it has to do both. Now carbon fiber is quite good at that, but in compression it suffers, and that's why you can't go very thin on the wall and make it withstand any kind of impact because it's got a weakness in its compressive side. So it doesn't take abrasion very well either. So boron, on the other hand, does take abrasion very well, and it's incredibly high compressive strength to weight ratio and compressive stiffness to weight ratio. These are two different things, by the way. So when you combine those into a tube, it's pretty amazing. They're just really quite expensive. So we came up with the Dragonfly in 2001, and it was at the time the lightest production bike, yet it also had the toughness of a normal frame. And that's right around when the Scott Addict came out, which was a super thin wall, large diameter carbon frame that was really fragile. Um, so that was sort of a similar weight, but not nearly as tough as the Dragonfly.
Well, to go a little bit deeper on this, so what is the what is the nature of the boron? Is it a molecule? Is it a filament? So you have carbon filaments. Is the boron is that, are you putting it into the resin? How is it commingled?
It's a filament, basically, a super thin wire.
And you're essentially commingling it in when you're creating the tubes, and then using
Mm.
the same resin to bond the entire structure together.
That's right.
Got it. And this is, if you were to add then, say, like graphene to the resin separately, it would be a compounding effect. I don't know if you have. I mean, I assume you've done
Yeah.
some stuff with graphene.
Yeah.
I've done a little bit.
Graphene is a really great material. It does improve the toughness of composites. It's again also very expensive to use in a whole tube. Usually it's used in smaller components, not so much on the whole frame. It's, its best use is in preventing the initiation of cracking. So it stops the micro cracking that starts with the failure mode. And that's a great thing. But if your laminate's too thin to begin with, all the graphene in the world isn't going to help you. So for really minor wax, it'll help. But for anything substantial, it's going to break anyway. So you have to start out with a thick enough laminate to get the toughness that you're looking for. Graphene is really great for highly stressed areas, which might start cracking from fatigue or just the design flaw of a stress concentration. So it's got a number of purposes. It's great for like pinch clamp areas, places where the mechanical stress is so high on a very localized area. So yeah, graphene's wonderful. We didn't get into it too much because it just wasn't practical for our applications and how we make the frames. But some companies have started using graphene, and it's pretty interesting stuff.
We did some experimentation with it early on and are looking at it for the future. And my understanding is, I haven't gone too deep into like the intermolecular physics, but it's essentially like you have a piece of paper, and if you start tearing the paper, that tear will propagate very easily. And then the graphene is almost like little tiny pieces of tape randomly and evenly distributed across the material that makes it so that fracture can no longer propagate in that direction, and it has to change direction where it bumps into another graphene molecule. And the graphene, essentially, when we tested, it was doubling the bond strength of the resin, so in terms of pulling apart the different layers of laminate, and then increasing the toughness of, say, a rim made with the exact same laminate in the exact same resin with 1% graphene per mass of resin,
Yep.
increasing the toughness of that rim structure by 20%, which is pretty
That's
cool.
right.
The
Yeah.
challenge is that it lowers the temperature, the glassification point of the resin. And so, a rim is like, there are, if you're going to put it on the back of your car, like, that's not a normal use case when you're riding, but, it's something that just makes it less resilient to those sorts of, people put it on the back of the car too close to the exhaust and they melt the rim. So we're having to experiment with some high temperature resins that have other issues.
Oh yeah, yeah. Rims are a great place for graphene just because they're in a place where you'll have some impacts. But yeah, temperature management is an issue. So yeah, that's the high temperature resins are another area that we're experimenting in, wrapping electric motor rotors with a high temperature resin and carbon wrap. So that's a whole other area, but I'm familiar with that stuff.
Which we'll
It's
get into in a second. Park that one because that's a fun theme. Yeah, and I'm just thinking about a rim structure. It seems like boron on the inside, graphene on the outside, to deal with like the
Hmm.
high compressive forces between the spokes and then the high impact forces on the external. We'll,
Yeah.
we'll
The material we use is called Hybor. You can look that up, Hybor. And they're actually coming back with new marketing efforts. I think the company got sold, and then the new buyers are revisiting how to spread the use of it. So they might be real interested in supporting a RIM project.
to be continued offline. All right. So then we've got your carbon fiber repair surface. We talked about the Dragonfly. It's a great segue into engineering and design philosophy. So let's talk about that.
Yeah. Well, it's to me, it's all about form follows function, and when something works so well functionally, it's going to look good. That's why trees look great just by themselves. That's coming back to the natural world. That's why we have a nautilus shell for our logo. It's the form follows function aspect of that just makes it look beautiful for some reason. You look at something from nature, you don't really know why is it beautiful. Well, the reason is the way it's structured, the way it's evolved over millions of years has resulted in the optimum structure. So for me, as a human being, artificially trying to recreate stuff that's been evolved in nature, I look closely at how nature does it first, and then I'll apply it to whatever I'm dealing with at the moment. And so that's how I design stuff.
There's the Nautilus shell example, like the golden ratio, and the way that really complex systems tend to evolve towards very simple, fundamental primitives of all design.
Yeah, yeah, yeah. There's some basic stuff that seem to apply everywhere.
So with your fiber repair service, so you started to see some of the problems with that were emerging with these large tube, thin wall designs that were being used to achieve a high strength or sorry, a high stiffness to weight, but then compromising in other areas. So let's talk about that.
Yeah, designing a carbon fiber bike is actually really quite difficult. There's so much going on. There's so many things you have to deal with, high stress areas that you can't really get around. There's there's a lot of constraints to designing a good bicycle frame. And then you're dealing with the tradition of how people clamp things on bikes, stem clamps and seat post clamps, and uh, that type of mentality is still with us with the carbon, which is carbon doesn't do well with. So a lot of companies struggle with that, and they'll come up with something that on paper or in their CAD model and their finite element analysis sort of works, but and then they go into the real world and they have to deal with real situations that they couldn't predict on the computer, and they get a problem with a minor handlebar whacking the top tube situation, which shouldn't really cause your bike to become dangerous, but in fact that's what happens. So you've got weak points or vulnerabilities in these really light frames. And if you're not expected to know what the vulnerability is as an end user, and you don't know that if you whack part of the bike in a minor way that you normally wouldn't expect to cause the frame to become uh, weak, then the whole design is a question. So you have to consider all these things when you design a bike, and a lot of companies have just depended on the computer and their finite element analysis to come up with shapes and designs that are inherently weak, and um, people get pretty disappointed when the minorest of incidents causes a crack in the frame, and if they keep riding the bike, the crack gets bigger, and then one day, I mean, most people decide to have it fixed before it gets to be a catastrophic situation, but it gets expensive, and you know, it's sad actually. Another motivation for getting into the repair business was to save the reputation of carbon fiber as a legitimate frame material. These types of things don't happen to thin wall titanium frames. A thin wall titanium frame will actually withstand a whole lot more abuse than a thin wall carbon frame. So it's just hard to make large diameter thin wall titanium frames that are stiff enough and not without problems of welding, the heat affected zones. So carbon fiber is a better material because it's so much easier to join and to mold. But if you have to design it properly to withstand normal abuse. And if you're not going to do that, then there should at least be a repair service available to keep those bikes from going to the landfill so frequently. And so that's what we do. We offer that, and we even train people how to do carbon repair service. So that's something we've done in order to keep bikes from just getting thrown away.
I think I've shared with you, I'm in the midst of doing a pretty radical ground up design, which is way off in the future. So I'll be picking your brain on that, but it immediately makes me think of the inherent compromises of current frame design and manufacturing techniques, including on our frame. And in our case, the way we've addressed that is through not, going with lower modulus carbon, T700, maybe some T800 in the frame, and then overbuilding it in order to have resiliency against impacts, but then also these sorts of micro voids and other imperfections that are an inherent process of any manufacturing system that involves hand laying of materials in a complex, 250 piece, layup. Like there's even that like human element that you have to design a whole bunch of fudge factor into to make sure that when mistakes are made, not if, but when mistakes are made, that there's so much overbuilding that they don't end up in a catastrophic failure.
That's right. Yeah, you have to have some safety margin.
And the mandrel spinning process that you were describing essentially eliminates a lot of that. And you're starting to see, with rims, that's the direction that rims are going in. Everything is going to be automated. It's going to be knit like a sock. And frames are a much more complex shape. But you're starting to see, actually, you probably know a lot more about the automation of frame design than I do. What do you see like as the endpoint, at least with regards to the like filament-based carbon fiber material in frames? Like where could it go with sufficiently advanced technology?
The robotics are getting super advanced now, and there's this technique called they just call it fiber placement or automated fiber placement, which is a fancy word for a robot arm winding fiber, on a mandrel or shape, and then compressing that and molding that. So it's where a robot will orient a single filament of carbon fiber continuously all around the shape that you're trying to make. They do that in aerospace now for really expensive rockets and satellite parts. But the technology is getting more accessible, and so robotic trimmers are another one. So we're getting ready to build our own robotic arm trimmer for resin transfer molded parts. That's where the edge of the part that you mold gets trimmed very carefully with a router. But imagine instead of just a router trimming an edge, you've got a robot arm with a spool of fiber on it, wrapping the fiber individually around the whole structure of the frame. No people involved, just someone to turn the machine on and then turn it off again. So that's kind of coming. That is a future. It hasn't arrived yet, certainly. Maybe for simpler parts, but frame is a very complex shape, so it'll take a while before they can get to that point.
It having to, being able to essentially spin a frame in one piece seems to be the ultimate end game.
Yeah, I think the genetically modified spiders would be a better way to go.
They might help us accelerate the design process.
Yeah, yeah. Just give them some good incentives, and they'll make you set a really incredibly strong, spider wound frame.
Well, it does. It speaks to the biggest challenge I see with that, which is you have to go around the shape, and so if you're going through a frame, like it's essentially the triangle is a ring, and so you need some way to like hand off the filament carrier from one side to the other constantly. Otherwise, you'd
Hmm.
just be able to spin it. It would be pretty straightforward. So maybe the frame comes in a couple of different sections that get bonded, but then those subsections don't form a ring, and so you can move them around instead of the machine in order to.
Well, there's these things called grippers. So the robot grips it, and then another arm lets go, and the other arm picks it up. And then there's like in weaving, there's this thing called the flying shuttle, which
Mhm.
my ancestors actually invented. It's where the shuttle that does
Yeah,
the warp drive.
your
It's
ancestors were
back
involved with the
back
flying
and
shuttle.
forth. Yeah, yeah,
That's one of the. All right, that's a whole other conversation.
yeah. That's a really interesting. I mean, it's the Draper Corporation. If you want to look it up,
I know Draper.
they were the Draper Manufacturing made the looms back in the Industrial Revolution in the Northeast,
Where
and
I'm sitting currently in Waltham, which was one of the first mill cities, not
yeah.
far from Lowell.
Yeah, so all those mills were our customers, and they would buy the Draper looms, and they were the automated looms with the flying shuttle was a big deal back then, and so they made a lot of those looms, and that's basically what sent me to college with a trust fund. So I
So
got lucky
you're a
on that.
trust fund baby.
Yep, yep, from
um,
inventors.
yeah.
Uh, but that's the world I came out of, and. So the idea of taking a spool of material and handing it off as you wrap around something is really not that difficult.
Okay, so then you can do it in a way that is resilient to probably 10,000 handoffs over the course of weaving a
Mhm.
frame, and you can expect that it's not going to fail once.
That's right. Yeah,
Oh, okay. All right.
that's
Then
not
that's
the hard
interesting.
part.
Got
The
it.
hard part is probably dealing with the resin and the forming and the getting
Hmm.
a nice surface finish.
Yep.
Those are the harder parts.
Yeah, and I'm thinking about SpaceX's attempts to create a giant carbon fiber fuel tank, and they
Hmm.
actually had to do the heating of the resin at the point of depositing of the filaments.
Yeah,
And that's a really
that's
challenging process because you can't build an autoclave big enough to contain a fuel tank for a giant rocket. Bicycles don't have that issue, but
right. Yeah, the filament winding technique, which is how all those tanks are made, is pretty amazing, and the large scale of those big rockets is phenomenal. I mean, there's a couple of places in Utah that make those, and it's just seeing such a large thing spinning and a fiber wrapping around it rapidly is really quite inspiring.
yeah, yeah, it's very very cool stuff. And that's again a whole nother thread about the Utah based composites industry that got its start in aerospace, advanced aerospace applications, which Envy and others came out of. It used to be Edge
Yep.
Composites, which you worked with Envy. You designed their tubes early on, right?
Well, yeah, the whole history behind Envy and Quality Composites back in the late 80s, literally, when I first came out to, actually, I think I ordered them in Massachusetts and took delivery in California. But it was Quality Composites out of Utah. Nancy Potash was the owner of that, also an MIT graduate who started roll wrapping carbon fiber in tubular form. And I'm pretty sure we were the first roll wrapped carbon tubes for bicycles that she made. And uh, that evolved to Edge Composites. So Quality Composites became McLean Quality Composites. And then McLean, the guys who broke away from that went to start Envy or Edge, I guess, which became Envy. So yeah, those same guys brought that technology, and we've been the customer ever since. And now there's yet another spin-off. The guys who are making the tubes at Envy have spun off and started their own company uh, in a cooperative venture with Envy. So they let them go basically, and we're working with those guys. So they're just following the top level of expertise.
Very interesting stuff.
Yeah.
So where else do we go in terms of I mean, this is about as deep composite, deep nerdery as we can get into composites and so on. And given that we're already here, we might as well just dig ourselves deeper.
Yeah. Well, so just on the roll wrapping, the thing that I remember one of the cool innovations that Nancy came up with was the double D section tube, where she would roll wrap two D-shaped tubes, stick them together, and do an outer wrap on the outside. So it was a incredibly efficient way to do a ribbed tube, or
Yeah.
with a single rib through the middle. She pretty much invented that. We started doing something with that on chainstays to get more stiffness out of a chainstay. But I just, for some reason, that image flashed in my mind about some of the innovative stuff that has been going on that people don't really see. And that's what I'm saying before, where the technology of composites has it's got a long way to go, and there's all kinds of stuff going on that is brand new.
Yeah.
Most people don't see it because it's all process oriented more than product oriented. But for guys like me, it's really fascinating.
Makes reminds me of a technology owned by a Taiwanese carbon frame manufacturer, pretty large scale tier one that I had spoken to, where they're doing that bracing inside of the forks. I don't think they're doing anything especially advanced in terms of how it's manufactured. I think they just have the inner, whether it's a bag or it's a EPS insert, and then they're just bridging between the two walls of the tube of the fork leg with another piece of carbon that gives it more lateral structure with zero impact on the fore aft compliance, which is a really cool
Yeah,
technique.
that sounds like Steve Lee at Gigantex.
This was YMA.
Oh, okay.
Yeah,
Yeah,
the Gigantex folks. I don't know if I've interacted with them yet, but yeah. Well,
yeah. There's some amazing innovation coming out of Taiwan.
yeah.
They're so deep into it. It's a fun place to go and see what they're up to.
This actually brings me back to I had a conversation with Russ at Path Less Pedaled, and he was asking tell me about the quality of stuff made over in Asia, and I was like, well, in fact, it's generally best to work with their production engineers because they're so close to the actual manufacturing techniques, and they're the ones innovating on those techniques. And in fact, even Specialized up until recently did not do carbon fiber in house. They outsource that. They do some of the work in house, but then the actual iteration design for manufacture and all that is being done by the factories, and rightfully so. The factories know it better, like being close to the ground. Though dealing with someone with yourself, you're someone who could go into a factory and be like, okay, let's innovate on this.
Yeah, yeah.
So then 2011, first production gravel bike.
Yeah. We came up with the adventure bike, we call it. It was also the first one that did the 650B tire size that can be used with a 700 by 42 or so. So mixing, going bigger tire sizes on a slightly smaller rim on the same bike as you'd run a 700C and 35 or 40 millimeter tire. So the adventure bike has been a real fun area for us as far as just developing a do everything, be everything bike.
And the geometry of that was kind of an endurance road geometry, right?
That's right. It was a road bike effectively, but with a few tweaks for riding off road.
So then this word gravel bike is kind of muddled. I never liked it, frankly. It's a marketing term. I remember it Specialized when we were doing the Diverge. It was still kind of honing in on what these bikes were. But you could argue that like, everyone's road bike was a gravel bike when you just put the biggest tires that would fit and ride it on dirt. But this concept of a one bike, it seems to be what you've pioneered. Like you can have a single bike that will be your road bike, perform, handle, give you that experience when you put road wheels on. But then you can put these big 650s on there and have an off-road crit machine that is highly competent in rough terrain. And
Yeah.
so yeah, that's very much my design philosophy, as you know, as well.
Yeah.
Fewer bikes that do more things.
Yeah, we have this kind of a marketing phrase for, how the N+1 concept, where, how many bikes do you need? Well, just one more than what you've got.
Mm-hmm.
Well, we did the N-1 concept with our mountain bike, which can also be a gravel bike or a adventure bike, but it allows you to change the head tube angle and use different fork travel suspension forks
Mm-hmm.
on the same frame. And of course, swapping wheels out is always a thing. So yeah, the N-1 concept where we just need less stuff.
So I reinvented that when I started thesis. We used to say like N-3, it replaces your
Yeah,
road bike, your gravel bike, your road bike, your cross bike, your light duty cross country bike, your adventure bike actually as well. Load these things up. Yeah, very much a philosophy that I think it's so good that despite its efforts to come up with new subcategories, for example, by having gravel bikes now run oversized 700 wheels and extending the geo and going with these really slack head angles in order to accommodate that wheel size. I actually think that the perfect form, the form that things want to evolve towards, is actually what you created in the first place, which is the one bike that does all the things and does them well. And depending on the wheels you put on them, will transform. And we've talked a little bit about geo changing,
oh yeah.
and things like this, which you have a bike that does that. Why don't we talk a bit about that and the technology behind it?
The Cephal, you mean,
Yeah.
where we change the geometry of the head tube
Mm-hmm.
and the bottom bracket to accommodate what you're using it for. Yeah, the concept there is if you're on a long ride, to be able to change the geometry of your bike mid-ride. So with an Allen wrench, you basically swap these flip plates out on your head tube area, and so you can climb with one geometry and descend with another. And to me, that's really fun because the climbing, if you're climbing up a long steep climb on a bike that you're going to descend, back down on, you really don't want the same geometry. You're compromising in one or the other. It either climbs great or it descends great. It's rarely both, or it really can't possibly be both because they're just doing two different things. So if you can swap out these flip plates and change the head tube angle, which is really all you need at that point, um, then you have a bike that climbs great and descends great. So for me, that was the goal of just making a better mountain bike.
Mm-hmm.
Um, the fact that it can be converted into other bikes for different disciplines is a whole nother angle. And you can even do that. Perhaps you wouldn't do it, on the trail, but let's say you show up, let's say you're on a trip, an adventure, maybe out to Utah, for example, where you're riding slick rock, but you're also going to go up, into the mountains. You might want to have different fork travels or different fork options. So you can bring a couple of different forks and swap out a fork, change your flip plates, and have a bike that's awesome for slick rock, and then another one that's awesome for the bike parks.
Mm-hmm.
So, to me, it would, but it's only one bike, and you don't need, three bikes. So that's the design result of a bike where you can change the head tube angle on.
And really, how much head tube angle adjustment is there on there?
Uh, it's a plus or minus 4 degrees.
Okay, so that's substantial.
That's a lot.
Yeah, that's transformative, really. I
Yeah,
work in increments of half a degree.
yeah. These are half-degree increments. Um, right now, 1 degree, but we can easily do half-degree increments. I find that 1 degree is really enough.
Yeah.
Especially when you have the option of tweaking the same bike. So the reason we focus on these half-degree increments on a production bike is to dial in the best compromise between two ways that it's going to be used.
Hmm.
When you don't need to compromise, you can go a full degree in the other direction and not worry about the fact that it's not going to perform as well, in super steep terrain because that flip chip is not the right one for the super steep scenario. Just change it out or flip it over to when you approach the really steep stuff.
And
So yeah,
it's applicable for mountain bikes particularly because the long slack geometries that have emerged in recent years make a ton of sense for mountain biking, especially descending. But when you're ascending, it ends up being so slack that you get wheel flop, you get the front end lifting, the bike naturally wants to tilt back. You don't have that on a gravel bike currently. And if you're not adding a huge suspension fork, you're never going to be descending terrain that is so technical that you need those slacked out angles. So it sounds like something that's very much could be applied to gravel bikes, but that, for the mountain bike application is actually pretty game changing.
yeah. Well, on gravel bikes or adventure bikes, uh, it's actually helpful if you're let's say you're a roadie and you're starting to go off road. And so you're driving these gravel trails, and then you're starting to get into more interesting off-road excursions with that same bike. But your experience on steep terrain is limited because you're a roadie. You're all your muscle memory and all your bike handling memory comes from the road and a little bit of dirt road stuff. Now you're kind of getting into serious off-road stuff, and you want to try a shortcut descent, down something kind of crazy. Let's say you're not very good at it in the beginning, and you take your time, and you don't have a bike that can go that fast down such a trail. Then you change it out as you get better at it, as you increase your skill level and your confidence level. You might want to go a little faster. So you want a bike that can go a little faster safely and go for that slack head angle, which is designed to get higher speed. So it's great for evolving skills and evolving terrain as you start exploring more radical stuff. So that's the other reason to do it.
Yeah, that makes a lot of sense. And in fact, what I'm working on going forward very much has a one of the core foci is being able to tailor the geometry as close to on the fly as possible.
Yeah.
I think if you want it to be on the fly, you're going to add a huge amount of added structure and complexity and weight. But having it be when you swap the wheels, there's very little to do. This sort of thing.
Yeah. Yeah. So yeah, the whole idea is to be able to go and have really fun adventures. After all, I wrote the book on adventures. See, here's this is the commercial part of our
Oh
plug.
wow.
Is this book I wrote about a trip I took back in the early '80s. It's a kind of it has nothing to do with bikes except that there is a section in there where I made a canteen out of bamboo in the Congo. But it's a pretty crazy trip, and I just called it Adventures. It's on
Um,
Amazon if anyone wants to buy it.
I will get a copy.
Yeah.
Very, very cool. We skipped over one, which is the Manta, which is another interesting innovation.
Yeah, suspension on a road bike. I mean, I keep saying that's going to be the future, and it hasn't happened yet, but I still believe that suspension road bikes will be the main type of bike being ridden in the highest levels of racing.
Oh,
It's
interesting. So you think suspension versus, say, wide, tubeless, aerodynamically optimized rims with a 30 mil tire run at lower pressures? You think the suspension has a sufficient benefit relative to that to offset, say, the structural complexity or weight?
Yes. So the big tire thing, the trend towards bigger tires is really a trend towards suspension. It's pneumatic suspension rather than mechanical suspension.
Well, as our regular listeners know, this is a topic that's very much near and dear to my heart. I talk often about the benefits of pneumatic suspension, So this will be an interesting place for us to stop and really dive in when we follow up in part 2 of this conversation, which Craig and I will be recording on the Thursday after this episode is published. So if you'd like to participate in the conversation, please tag us in the ridership, direct your questions and comments our way, and we will try to incorporate them into part 2. And of course, if you haven't already, come join us in the ridership. We'd love to have you, and there's a lot of innovation that'll be happening there in terms of how we use new digital tools in order to facilitate the community that we want for offline connection, exchange, and experience. So with that, until next time, as Craig would say, here's to getting some dirt under your wheels.